Ai, que a gente caindo também.
All right, good morning, everyone. Yeah. Okay. I think today I just wanted to start to see if there's any questions about the project. All right. Well, if no one's saying anything, then I guess there's no questions. Let me pull up Miro here. Okay. All right. Sorry, that took a couple minutes. All right, here we go. All right, so today what we're going to discuss is the minimum spanning tree. And the algorithm everyone knows is usually Kruskals, but there's actually like a family of algorithms. So kind of discuss them all. So today is the 13th and I'm on the right board. Okay, super. Minimum, oops. Okay, so we're given a weighted graph. We'll call it G. And the weight function. The book uses W, but I usually use omegas. Okay. Sometimes people consider G to be the triple, the two sets plus the function. Find or we want a spanning tree. T of G such that the following is minimized. Weight of T, which is equal to the sum of the edges in the edge set for the tree. Let's say here, note, let's say T is equal to VT comma ET of the weight of the edge. Yeah. So question, is the minimum spanning tree always unique? And I'll say why or why not. If you say it's unique, we need a proof. If we say why not, we need a counterexample.
The minimum spanning tree is not always unique because we have just like a triangle where like you have 3 nodes and 3 edges, and each edge has a weight of 1. You can use any 2 edges.
Okay, yeah. So I'll just put this here. Why not? No. Here's an example. One, one, one. And this has 3 spanning trees. Has 3. Okay. Now, however, there are cases where we could say it's unique, and this is, let's say, lemma 7.1 of the textbook, which states that if all edges of a connected weighted graph have distinct values, then the graph, oops, I can be a little more precise here, then G has a unique minimum spanning tree. All right, and the thing we want to look at here, question, is the converse of lemma 7.1 true? Why or why not? Okay, and again, if so, the first thing you need to do is define what the converse is of that statement. And then if the converse is true, we need a proof. If it's not true, let's look at a counterexample. a lot of times proofs of natural are easier, so hopefully that's the one, right? All right, so I'll put you in groups so you can kind of start thinking about this. And I guess if you get through that, the next thing that we'll do, if finished, try to prove lemma 7.1. Okay, so when we come back as a group, that's what we'll work on proving together. Let's open the rooms. Oh, we have low attendance today. I'll try it with just 7 rooms.
Hello?
Hello?
Hey,
Okay, we'll claim a board.
um, anyone have some initial thoughts on the question? Yeah, she wrote it. It was the last thing on the lecture slide.
I'm just writing the converse down.
Yeah. Unique mineral spanning tree.
Do we think the converse is true or not?
I want to say that it is, but I feel like I'm just trying to think about like if there's any possibilities that it isn't.
All edges have distinct values. I'm like going through my head trying to think of different graphs that could break this. Um, well, what sort of proof can we make for this? Suppose the group next to us to our left put false. Fair enough, yeah. Um, prove by counterexample. So assume it's false. Or not counterexample. I think so.
Yeah. The like least amount of weight you can use to do it, I guess.
Yeah. Mm-hmm. Yeah. I mean, if it didn't have distinct values, then you could have multiple minimum spanning trees.
Yeah.
So we just say, assume this isn't true, then we can have a graph in which there aren't distinct values, which means that we could have potentially multiple different minimum spanning trees. Therefore, we have a contradiction, so it must be true. Right?
Sounds right.
Makes sense to me.
Alrighty.
Yeah, because even if it had repeating values, it was gonna have to be unique anyway, because it's not like it would choose the higher value when comparing the different repeated values to the different values on the graph. Yeah.
Alrighty, who wants to write it down? Hence why I asked, because I'm in the same boat.
False.
Need to make a counter example.
Wait, how did we arrive that it was false? I thought it was true. Right. Right. Mhm. Yeah, if it's false, we can just draw a little graph. Oh, no one can draw with a mouse.
That circle is prime. Looks like a diamond.
Dang.
Even running Miro on my Mac seems to like overheat. And I don't know if it's like sucking like immense amounts of freaking. I don't know.
Hmm. Um,
I don't know.
I mean, the group to our right is using 3 nodes in a line.
Oh man.
Well, what are the 2 minimum spanning trees in there? Which would mean that it has a unique minimum spanning tree.
Change one of the numbers to be the same value, right?
The breakout room is closing, by the way.
Oh, what?
So that could work. Yeah. Alrighty.
I believe 5 seconds.
See you guys back in the main room.
From the looks of it, you guys were all having good conversations because usually I have people come back faster. Not as many people wait to be kicked out. That's good. Anyway, so what about the converse? First of all, what is the converse of this statement?
If it has a unique, if a graph has a unique MST, then all the edge weights are distinct.
Yeah.
Have distinct values.
Yeah, and so actually, if a weighted graph G has a unique minimum spanning tree, then all of the weights.
Oh, I didn't even notice the room closed.
Oh, sorry about that. Maybe they changed the notification. On the edges are distinct. And what's our vote? Is it true or not true?
Not true.
Great. Not true. I feel so next semester I'll teach 246, the discrete math class. And I feel when students encounter converse for the first time, that it kind of throws you for a bit, especially if it's something that you think should be an if and only if statement. Even if it just says if then, you kind of imply that you need both directions. All right, who's good? Can someone draw the counter example that you have then?
A really simple one, I think, would just be putting 3 nodes in a line, and I'm happy to draw it. And
Okay.
then connecting them with 2 edges that have the same weight.
Great.
But
But you.
we were also talking about to like more generally say that you could have 3 different subgraphs connected with 2 bridges that are only that's one, the only way to move from one subgraph to another. Therefore, you have to take both bridges to get through the whole graph. And
Yeah.
if either of those bridges, or if those 2 bridges have the same value, then you can have a unique minimum spanning tree that's taking both bridges and therefore having the same value.
We can, any tree is a unique minimum spanning tree. And then I'll put here, all bridges can have the same value. I just put V's in there so that this is subgraph 1. Here's subgraph 2. Subgraph 3. E1 goes between these 2. E2 goes between these 2. Well, that wouldn't disconnect the graph. Yeah, so something like this. And Ben, do you want to give your example that your group came up with?
Yeah. So we were sort of thinking, so say you had, I don't know, just some cycle, and then you had some edge in that cycle that was like huge, way bigger than all the other ones. And then you just had some node that was sticking off of the cycle somewhere, that had like a repeat smaller value for a weighted edge. So our example was a cycle that had edges 1, 2, and 57. And then we just have another edge that's like sticking off, that has a weight of 1. That's the minimum spanning tree, certainly, and it's unique, but not all of the edges have distinct values.
Yeah, so what I'm going to go kind of generalize this. I drew another example, so if you want to see the one that Ben said with the triangle. We have exactly as Ben said, a cycle with one edge with a really high weight, so we know that we don't need that weight, which actually comes into something else. Maybe I'll just put this here as a claim. It needs maybe a proof. And then we add some stuff to it. So I'm just calling it dangly things, right? So if we have our graph anytime you add these dangly things that are like paths leaving it, right, which are bridges too, that it's also tree-like, right? We know that we need it. So let's put our claim here. This brought up this claim that if alpha is a cycle in G, and we'll say it's okay. It's a weighted graph. And here, okay, so I usually think of a cycle as a sum of the edges. Jeff thinks of it as a sum of the vertices, but we can know that there's induced edges that come between them. What are we saying here? Then we'll call it E max, which is defined to be the maximum, I guess it's argmax, over all edges in alpha of the weight of the edge. Okay. Is not in the minimum spanning tree. And actually, and we'll assume edge weights are distinct. Okay. And the reason why we can kind of think about this, right? If this edge goes from U to V, right, there's two ways to go there, right? And the one way is through this thing with 500. And the other way is through the whole other path, right? Now, and we kind of need to say that we need to have, we can't have all of those. We know for sure we can't have all of them because we need a tree, right? And so going the other way around is what's going to work better, right? It still needs a proof, but and there's another thing that we can say. We'll say E min, arg min of W of E, E and alpha. The guess would be that it's in the minimum spanning tree. Right. But this is less clear, so I'll leave a question here for you to think about, but is this true? Okay. Put why or why not. Okay. Well, let's go over to the claim that we have today. No questions for. So lemma 7.1 says if all edges are a connected weighted graph of a connected weighted graph G have distinct values, then G has a unique minimum spanning tree. When I see a proof like this, how do you want to start the proof?
You might think that it's going to be a proof by induction, so you can find a really simple base case. or a really simple example of it that you could use as a base case maybe.
Okay, and what do you want to induct on?
Adding more nodes to the tree. Or to the graph, sorry.
The number of vertices in the graph?
Yeah.
Okay. I haven't tried to prove this by induction, so let me think of how that would work. So then if we assume that a graph, let's think quickly about our inductive step here. We assume a graph on n minus 1 vertices, if it has distinct values, then the minimum spanning tree is unique. And now we have a graph on n vertices. We would maybe choose one to remove along with its incident edges. We have a unique minimum spanning tree. But adding that vertex back, that unique spanning tree might not be a subset of the spanning tree. So which vertex would we want to remove to make a smaller graph? Do you know?
Not really, no.
Okay, I'm going to leave this here as a challenge because I think you can do it this way. One option, and this is always a good thing to try with try induction. We won't do that now, though. Okay. Whenever there's graphs, because we have the number of nodes or the number of edges you can induct on. And it's a good technique to try to think about the graphs here. So let's do the other way we can go about this is we can assume by contradiction that we have two minimum spanning trees, T and T prime, say. Okay, and also whenever, in general, when I see a uniqueness claim, the gut instinct of the way to prove it is to say, okay, let's assume this isn't true, and then leads to some contradiction, right? Now, often you want to, I guess, the prettier proofs are the ones that are not necessarily by contradiction, but kind of building up to it. But once you have that contradiction proof, you can, I guess, rework the proof you have to be more constructive than the contradiction. But okay, so we're going to assume that we have two minimum spanning trees, T and T prime. Okay. And so we'll just to give ourselves T set of vertices and edges, T prime, same set of vertices, different set of edges. Okay. And just to make it easy, I'll just say the graph is the vertices and the edges in the graph. Just to give all of us things to work with. And our weight function goes from, I just did you the R's, has distinct values. Oh, actually, you know what? There's a word for that. It's injective. now that we have these two different sets, these two different graphs, right? What I'm going to do is okay. So let's choose an edge in their difference. So I'll just say E minus E prime union E prime minus E. Be of minimal weight. So of all of the edges in their symmetric difference, just we're gonna choose this one, right? Now, now I can say without loss of generality, assume E is in E minus E prime. Okay. So that implies, right, we'll just spell it out a little bit here, is that E is in T, but E is not in T prime. Right. Now, what happens here?
Sorry, I have a question.
Yeah.
So this thing here, the E minus E prime union of E prime minus E, is that saying that it's all the edges that are in E but not in E prime and also in E prime but not in E? Or I don't really get what that means.
This is the symmetric difference. Right, and I'm taking the union, not the intersection. So I take all the edges in E, but not in E prime. That's one set. I take the edges in E prime, not in E. That's the second set. So first set, second set, and I take the union of those two sets.
Oh, I see.
Yeah.
All the edges which are only in one.
Mm-hmm. Yeah, sometimes there's a nice symbol for symmetric difference. It's like a triangle looking thing, but I feel like everyone always forgets what that means. So.
Thank you.
Okay. Yeah, and don't hesitate to ask because then it's harder to follow the proof going on if we don't know what's going on, right? Okay, so assume that, okay, so I'm assuming that it's in this first set, right? Because here's the set 1, here's the set 2, right? If E is in this set, it's in one of them, but not the other, right? And that's just the way these sets are defined. And yeah, because if it's in the union, it has to be in at least one of them. Okay. And so now we know that E is in T, but E is not in T prime. Okay. So let's just add E to the T prime. So let's call T double prime is equal to T union E. Okay. Well, is this a tree any longer? Example. So it could have we'll say this is E. We'll claim that the first E is in E, but not T prime. Oops. Listen, that one's T. Got another one here. Here's T prime. Okay, and then by construction, we'll call it E prime. E is in T minus T, I guess E prime. E prime is in E prime minus E. So we'll call this set S. So S is equal to E prime. Right? And we know by construction, or by definition, right, the weight of E is strictly less than the weight of E prime. Okay, we know that's true because we've chosen E to minimize it, and we know that they have distinct values. Okay. Now, if I look at, put this in pink here, T prime union this edge E, well, what I have is this whole graph again, right? Well, in general, it might not be the whole graph, but in this case, it's just a small example, so it is the whole graph. So I guess maybe to make sure that it's clear, maybe I'll add one more edge here. Okay, so it's not the whole graph now. This is no longer a tree. Okay, and I think was it chapter 5, exercise 1, we're trying to prove equivalence of different definitions of trees. Once we prove the different definitions of trees, we can kind of use those definitions interchangeably. We're working towards that right now. Okay. So we have something that's no longer a tree, right? But, and why is this? Then if we say that, we'll just say let E be the edge between U and V. Okay, then there was a path from U to V in T, right? Adding E creates a cycle. Okay. Now, let's see, we'll call it a path P. Okay. But I know that every edge in P, every edge in P must be in T. Oops, this should be T prime. It must be in T prime. Did I do this wrong? Oh, yeah. This didn't correct me here. Aha. So T prime doesn't use E and T doesn't use E prime. Okay, so every edge in P must be in T prime, right? Because the only thing I did was add the edge E. And since E is in T, we know that there must exist an edge, we'll call it E prime, in P such that E prime is not in T. Right? Otherwise, T would have every of one of these, and T would have the cycle. Say otherwise, T would have a cycle. Have the cycle P union E prime. Okay. Now, and conveniently I've already labeled this. Note, by choice of E, the weight of E is strictly less than the weight of E prime. Okay, and we'll call this T triple prime is equal to, make these define signs, T double prime minus E prime, right? So this is equal to T prime union E, all of that minus E prime. Is a spanning tree of weight of T prime, we add the edge E, plus the weight of E minus the weight of E prime, and this is negative, which implies the weight of T triple prime is strictly less than the weight of T prime, which is a contradiction. Do you have any questions on the steps there?
In the notes, you said that every edge in P must be in T prime. Where is P defined? What's P?
Here we go. There was a path P from U to V in T.
I see.
Oh,
thank
this,
you.
sorry, this should say T prime. Right, so E was an edge in T, right? It connects U to V. We know that in any spanning tree that U and V have to be connected. So find the way that they're connected in T prime. When I add E, now I have a cycle. Super. All right. And maybe now we, okay, so this is a slightly different proof than within the textbook. So if you want a different spin on the proof, you can go look there too. Another thing we want to, the book does next is they look at tie breaking. So let's discuss this. Say here that it would be convenient if we could have, oops, thanks, Nathan. Tie is broken in such a way that the minimum spanning tree was always unique. Right, because then we can talk about the minimum spanning tree, and we could talk about properties of this specific thing rather than having it be a little more ambiguous. I'll say makes things more concrete. So we could either just assume that all the edge weights are unique and then we know that there's a unique minimum spanning tree, or we can have a tie-breaking rule. And why does this tie-breaking rule work? So let's define something. My hair is falling out. Okay. So a partial order on a set, say E, is an assignment to each pair E1, E2, and E, one of three relationships. Right? E1 is less than E2, E2 is less than E1, or E1 equals E2. Okay, and if we do this relationship, and you know what? I'll define it more formally, maybe. Is a relation, just call it a relation there, less than or equal to, and I made this kind of a funny one just so it's clear that it's a comparison thing, such that for all E1, E2 in E squared, either E1 is less than E2 or E2 is less than E1. I could say or both. In which case we say that they're equal if both of those relations hold. Right. Now, if I have e.g., this can be defined by edge weights. So E1, E2, E3, and we'll say the weight of E1 is 1. Yeah, I'll just put them in different colors so I have less going on here. 1, 2, 2, the weights. So we have E1 is less than E2, E1 is less than E3, E2 is less than or equal to E3, E3 is less than or equal to E2. Right. And so this doesn't give us a total order, right? Because really we can't differentiate between E1 and E2. So a total order a set E is totally ordered if for all distinct pairs, oh, this yeah, so this is a, for it to be a relation, it has to satisfy like transitivity and stuff. But so totally ordered if all distinct pairs either satisfy E1 is less than E2 or E2 is less than E1, but not both. Okay, and if we have a total order, so e.g. add a tie-breaking rule, and we'll put this here, consistent. Okay, and we can define E I, let's do this, less than or equal to EJ if weight of EI is strictly less than the weight of EJ. I'm going to take this out, just put this one. If the weights are equal, right? But we'll say that, and we're in an undirected graph, so EI well, no, it wouldn't be let because we already have EI. Say EI is equal to VW. That the index of V is less than the index of W. And EJ is equal to UX such that the ID of U is less than the ID of X. Okay. So here we're going to use these IDs of them to be unique to help this tie breaking. If the vertices are the same, or sorry, the vertices can't be the same. If instead I had EI is equal to WV, if we're in an undirected graph, WV is equal to VW. So we can just label it this way. And we'll say the ID of V is less than the ID of U, or the weights are equal and ID of V equals ID of U, and ID of W is strictly less than the ID of X. So we can use this to break the tie. Another way you could do it is you could use IDs of your edges. This is the way that Jeff Erickson presented, so that's what we're kind of doing here. Then, using this total order, we can, we would have a unique minimal spanning tree. Okay, so that's why in the book he's talking about the minimum spanning tree. The book talks about the minimum spanning tree. Okay, so that was slightly a bit of an aside, but this is also helpful because we think about these partial orders and total orders come up a couple times, right? Because we have a pigeon problem right now that some of you are thinking about. Topological sweep, we have partially ordered things. And I don't know, I think they're kind of fun to think about, these partially ordered sets. But let's go through this generic algorithm, and we have about the time for that. So let's see. Yeah, we'll just call it generic minimum spanning tree algorithm. And it's to iteratively add edges to, oh wait, you know what? Start with an empty one, right? With F equal to the empty set. And we'll put here, will eventually be our minimum spanning tree. And then iteratively add edges to F, maintaining the loop invariant that F is a subtree or a subgraph of the minimum spanning tree, i.e. F is a partial, is a forest, and okay, maybe not IE, I'll just say note. Okay. If any, who was at Catherine Hess's talk yesterday? Anyone here? No. She gave a wrong definition of a tree. Or the tree that she was defining. Yeah. So if you were there, challenged to figure out what that was. So there's 3 versions that the, okay. The first is to add all we'll say safe edges. That is those, you know what, put this here. And recurse, where a safe edge is a minimum edge leaving a component or a tree of F. In this, okay, to spell this name right, is known as Boru. This is one of the first, predates other algorithms. And the fastest MSTs are variants of this. So really this is the first and essentially the best, and I'd say variants kind of very loosely here because it's actually pretty close to this. And then the other one is what's known as Prim's algorithm. So F is a tree and add its safe edge. Right, so add the smallest weight edge leaving the tree, right? And this is Jarnik Prim. And then the third one is probably the one that's most common, is sort all edges and iterate in order. If not creating a cycle, add the edge. Otherwise, skip it. Okay, and this is Cruise Cow. And this is going to use something called the union find data structure. And that's what we'll talk about next time. Do you have any questions about the generic kind of way to find a minimum spanning tree?
Would you classify these as greedy algorithms in the sense that they're taking the safest and kind of building up from that?
So typically when you're looking at greedy algorithms, you're not doing, so we could think of it like a really dumb greedy algorithm, right? Which is just add an edge, if it's still a tree, keep adding it, right? Otherwise ignore. But these are like slightly smarter versions of a greedy algorithm. So I would say that they're greedy algorithms, but there's maybe more structure than a typical greedy algorithm. Yeah, that makes sense.
Thank you.
Mm-hmm. All right, well, thank you all, and I'll see you on Thursday. And I'm here if there's any questions. Yeah, you too.
Oh, I actually do have a quick question.
Uh-huh.
So for problem 1 for the upcoming assignment so I'm only capable of doing 9 right now. Am I going to not pass it, missing that one, or is this one different than the last one in some other sense?
Well, we graded holistically, right?
Makes sense.
So I would still do 10, try to keep them spaced out as possible, and then make a note that this one, like this last one, violates this rule, right?
All right, gotcha.
Yeah, as long as your things are substantial enough, then I think.
All right, cool. Thank you. Have a wonderful day.